Good day, everybody. I guess this is a slightly interesting problem from Sierpinski's number theory textbook. It's problem number 70, and it says find all arithmetic progressions. This is a lot of times called sequences these days, right? I'll abbreviate that with SEQ here. Okay, so it's the same as a sequence, arithmetic sequence. Now, so we're saying find all arithmetic progression sequences with a common difference. He said they used the word just difference back then, but these days they call it common difference. I'll say CD, common difference, okay, of 10. Now let's write some examples here. It says of more than two prime numbers, right? More than two prime numbers. Well, let's start out kind of low. You can look at 19, it's a prime number. And if you add 10 to 19, you get 29. Right? So right now we have an arithmetic sequence comprised two numbers with a common difference of 10. Okay? Now let's see what happens if we add 10 to 29. We get 39. Now notice that 39 is not a prime number. It's equal to 3 times 13. So 39 is not prime. So it says find all arithmetic. So you see, so this is kind of interesting. So what's going on? Is this common? Let's try another example. Maybe, let's see, 73. 73 is prime, isn't it? 83, right, is prime. You get to 93, and once again you have something that is divisible by 3. 93 is not prime. It's 3 times 31, right? So both of these underlined objects are composite numbers, i.e. not prime. Okay, so this is kind of interesting. Are there any, in fact? So you see, that's the interesting. We've tried these two cases, and it didn't work out, right? They had exactly two prime numbers, but not more than two prime numbers, okay? Now, let's take a look at kind of the structure of this. An arithmetic sequence would be in this form, right? N plus 10, n plus 20, n, of course, being a natural number or just an integer. Okay, now this is a claim. It's not too difficult to see. Exactly one of these numbers is divisible by 3. Now the way I've written it, it's always the last number, but I don't know if that's always really the case. But now notice if we take a look at this modulo 3, it's not hard. I'll just spend a little bit of time proving this. If we look at this mod 3, meaning replace all the numbers with their remainder when you divide by 3 is what that actually means. So n's not going to change, of course. We don't know what it is even. Now, 10 leaves a remainder of 1, right? So we're left with n plus 1. Okay, and then 20 leaves a remainder of 2, so modulo 3, that's n plus 2. And now it's very clear one of these numbers has to be divisible by 3, right? Because this is 3 consecutive numbers, okay? So that proves the lemma, right? So it gives us a means to think of the very first one. Well, the smallest odd prime number is divisible by 3, right? Okay, so if you take a look at this guy down here, 3, you see we start with 3, all right, and then the next one will be what, 13? And then the next one would be 23, and voila, we do have a sequence, an arithmetic sequence, common difference 10, comprised of prime numbers, right? You see, so this checks the box. Okay, 3, 13, 23. Okay, now I go off here, I say, moreover, this has to be the only arithmetic progression, AP, not advanced placement, since all others would have a term divisible by 3, right? See, it's okay to have a term divisible by 3 here because 3 happens to be a prime number. Okay, but any other number divisible by 3 cannot be a prime number because it has a number strictly between 1 and the number that divides it. Okay, so this is the only one. So there is exactly one, folks. There's exactly one. It would be the answer. Okay, so let's come back up here and just says find all arithmetic progressions, common difference 10, formed of more than 2 primes. Well, the only one would be 3. Now I'm guessing that a lot of you can just by inspection see this fairly quickly, but proving that this is the only one is more of a task. Okay, I'm not saying it's super difficult, but so we have 3, 13, and 23, right? This is the only one. So again, not to sound like a broken record here, most viewers would have discovered this in the first 15 seconds, right? This is an arithmetic progression, common difference 10, all right? But that's all you got. There's more work to do, and that's to establish, are there any others? And the answer is no. There's no others. 3, 13, and 23 is the only arithmetic progression, common difference 10, formed of more than 2 primes. So that's all, folks. I thought, again, it's slightly interesting because you have to do a little bit of modular arithmetic work right here to reduce these guys mod 3. Realize you get consecutive numbers. Realize one of them has to be a multiple of 3. And so that just is incontrovertibly proves that 3, 13, 23 is the only such arithmetic sequence with said property. Okay. Till next time.